we get to now is geometric progression. Geometric progression. All right. So in AP we saw that it's in the format such that it's A and then A plus T and then A plus 2D, A plus 3D, right? So in AP we were sort of adding and or subtracting depending on what D is. In geometric progression, what we're doing is we're multiplying. So if I tell you that okay, there's some sequence 1, 2, 4, 8, 16, you'll probably realize that what I'm basically doing is I'm multiplying the term by 2 to get to the next term. So if I take the first term multiply by 2, I get to the second term. If I take the second term multiply by 2, I'll get to the third term. And this is consistent throughout the series. So this is something that we call a geometric progression. Whenever you're multiplying by something to get to the next term consistently, that's what a geometric progression is. So just like I did for arithmetic progression, geometric progression can also be written as a times r squared, and so on, where a is your starting number 1 and r is the number you are multiplying by. In this case, you're multiplying by 2. So a is your first number, b r is your tn plus 1 divided by tn, or you could say tn divided by tn minus 1. Basically, term divided by previous term gives you r. And if you want to see it on a number line with our frog, is basically starting from 1, it jumps 2, right? It jumps multiplied by 2, so it jumps just 1, and then it jumps multiplied by 2 or plus 3, it lands at 4, and its jumps are increasing as they go, right? So I've already given it here, but any nth term can be represented as a times r n minus 1. And this is very similar to AP because you just start with your number a, and then if you want to get to the nth term, you would be multiplying it by r, right? And these are, there will be n minus one of them, right? Because one of the numbers is a. So when you're multiplying, you are multiplying by r n minus one times, and repetitive multiplication can be just be represented as power. So it's a times r to the power n minus one. This is your term formula. Secondly, there's the sum formula. So the sum of the first n terms in a geometric progression is a times 1 minus rn. The power n is to r, not to 1 minus r as a whole thing. So let's put a bracket there and 1 minus r. Okay, so just to show you a proof of why the sum of geometric progression is like this. So what Sn basically means is that you take a and then you add ar and then you add ar squared all the way till arn minus 1, right? So what if I multiply it by r? I'm just writing a new statement. This would be, well, if a is multiplied by r, it would be ar. If ar is multiplied by r, it would be ar squared, ar cubed, all the way till arn, right? So arn minus 1 plus arn, right? So if I do Sn minus r times Sn, right? So essentially this is 1, this is 2. I'm minusing 1 minus 2, right? So, well, here again I can pair such that the terms cancel out. So if I pair AR with AR over here, AR minus AR would just be 0, right? And then AR squared minus AR squared 0, AR cubed 0, and I can do this all the way till ARn minus 1, right? And after I do this, I am left with ARn because there's no ARn over here, so ARn is left, and A is also left because there was no A here. So what I'm left with is A minus ARn. And if the rest is just algebra, I can take Sn common. So it becomes 1 minus r. This is equal to, let's take a common here, 1 minus a minus, sorry, 1 minus Rn, and just push this into the denominator, we get our formula. Right. So this was a short proof to convince you sort of that, okay, this is actually true. Right. So the last bit of geometric progression that we're left with is sum to infinity. Infin infinity. Right. The formula for sum to infinity is a over 1 minus r, but this is not actually a new formula. This is sort of the simpler version of the previous one, right? So the first thing that you'd have to agree with is that if I have any number, right, let's just take any number a, and if I have any number b, right? So, first of all, if b is the larger b gets, the larger the denominator gets, the smaller the whole fraction will be, right? And if b is infinity, then anything divided by infinity is zero, right? This is something you'd have to agree with. So, what sum to infinity basically means is that for that certain geometric progression, what is the sum that the series will approach? And in order for anything to have a sum to infinity, its common ratio r must be between -1 and 1. Right? The importance of r being -1 to 1 is that whenever you're multiplying by r, the magnitude of your next term keeps on decreasing, right? So if I take a look at the numbers between -1 to 1 on a more basic view, it is that it will be a fraction such that the magnitude of the denominator is greater than the magnitude of the numerator. It may be something like 2 over 3 minus 2 over 3 or whatever you can think of. But basically the magnitude or the absolute value of d is greater than that of n, right? So if I have any number such if I have any fraction such that the degree is a bigger number, right, and I am raising it to some power, so as I increase my power, the denominator will increase more than will the numerator, and hence this whole value will become lesser and lesser as x becomes larger and larger. And the limit as x approaches infinity will be 0 because you'll eventually get some number divided by infinity, it will be 0, right? So as you're multiplying more by r, as your power is increasing, your value is become smaller and smaller, and eventually it is approaching 0 at as the power approaches and as the power approaches infinity, yeah. So let's take an example. Let's say 1/2, 1/4, 1/8, 1/16, and so on. Now what I'm doing is I'm starting by 1. My R will be 1 over 2, which is definitely between this range. So this is a series that will converge to some value. And again, multiplied by half, multiplied by half. So here my A is 1, right? My R is 1 over 2. And what if I ask you to find the sum to infinity? Now the formula for sum to infinity is a bit different than the normal, but it's actually the same because when I write it like this, 1 minus R, sum to infinity is basically the sum when the nth term is approaching infinity, right? When the nth term is becoming larger and larger. And if n is over here in power, right? So if you're raising your r to the power n as explained over here, this will become 0. When n is infinite, when n is approaching infinity, this number is becoming 0. Since this number is becoming 0, you just get a 1 minus 0 over 1 minus r, which is just a over 1 minus r. Right. So here a is 1 and r is half. So 1 minus half, this will give me 2. Right? And what this saying is that 1 plus half plus 1/4 plus 1/8, and all the way you can go, the more you are adding up the terms, the closer you will get to 2, right? And if you could somehow keep on adding all the way to infinity, you will get to 2. And it might, if you're listening to this the first time, if you're coming across this the first time, it might sound a bit weird that you're adding an infinite number of terms. How can you get to a fixed value? Shouldn't it always increase? But what you'd have to agree with is that the terms are getting smaller and smaller, and as you go more, as you're increasing your number of terms, your number is becoming so small and it's contributing very less to the total sum. And for the specific for the specific what should I say? For this specific example, I could also give you a bit of a visual of it. So let's say there's a block. Let's say there's a block of, oops. Let's say there's a block and it has the area 1, right? So to 1, you add a half, right? So let's say it looks something like this. And then to the half, you add a fourth, so half of this. And to the fourth, you add a eighth, so the half of this. Right? So this is half, this is fourth, this is eighth, and then half of this, 16th, half of this, whatever, 32. So as I'm adding or as I'm chopping finer and finer pieces, you'll realize that I'm getting closer and closer to completing this big picture that has the area of 2. Right? It might not look like that much because this is not really drawn to scale, but as I'm putting more and more pieces in, my gap between two is getting shorter and shorter. I'm reaching some value 2. So I will keep this, keep this, keep this, keep this, keep this, keep this. But eventually, if I could go on to infinity, I will reach the value 2, as in this whole piece of paper would have the area 2. Right. And that's all there is to it, to APGP, right? Not a lot to it, it's a small chapter. Anyways, bye bye.